All right. So again, so back to the 2014 FRQs. Are there questions about number 2? I want to go over that integral for sure.
Yeah.
So are there questions, I guess, on anything on A through D? Do D as well?
I just have a general question.
Shoot.
When it says velocity, yeah, like it says for D, it says gravity expression for the magnitude of the tangential acceleration of the block. It says magnitude of the tangential acceleration, but the answer says negative. Would I be taken off if I got a positive?
I do not believe so.
I think it's
Magnitude.
It says something magnitude about absolute value.
Oh, I didn't read it. Okay. Okay, and that goes the same for like if it says magnitude or velocity as well.
Yeah. Anytime it says magnitude, you don't need to worry about your negatives. But I will say that's a perfect example of a problem where, although the magnitude is a positive value, to correctly move forward with that problem, you have to take that negative into account.
Yeah.
Do you know what I mean?
Yeah.
My understanding is if you put a negative in, they wouldn't take the points off.
Okay.
Is what I've seen on a lot of these.
Okay.
Cool.
Okay. Yep.
On the problems where it asks you to, so what question was it? Too many papers. Part B, Roman numeral 2. Sorry, that's 2016. Part B, Roman numeral 2. On the figure below, draw an arrow starting on the block to indicate the direction of the horizontal component of the net force on the block moving when it's at the position shown. It wants just one arrow, not the components, which is weird to me. That's what they want. Okay? So what I would do, I honestly, when I did mine, I wrote 2. I drew it once with components, you know, and then I made a little drawing next to it that showed the resultant force. Okay? Because the drawing with the components will help you make the justification. And it says justify your answer.
If your drawing has the components and the resultant, that's what you get marked down for that.
Well, let me see what the, again, because I've never, let's see. For drawing a single arrow pointing into the third quadrant is 1 point, or 2 points, which is crazy to me. You know, that seems weird to me that they would, like, that's 2 points off for drawing those components in. I'm going to the AP conference this summer, that doesn't help you guys any, so I'm sorry, I don't know. I would err on the side of everyone that I've seen where it's asked you to draw a force, it wants the force, not the components. Follow? Okay. And then make sure that your justifications are well worded, right? There must be a force pointing to the left to provide the centripetal force, and friction is slowing it down, and so that'll point backwards or down, or however you want to word that. But cool. All right. So any problems with A through C? Okay. So let's jump ahead then and do part D. Okay. So 2014, number 2D. So let's see. So here's what we have discovered so far. I'm just going to kind of summarize real quick because we might need some of this. In part A, we figured out that the height at the top of the ramp had to be an expression that was equal to VO squared over 2G. Oh, incidentally, you guys, on tests, I've done problems like this where I've said, write expression for, and some of you keep putting 9.8 in instead of G. Don't do that. Leave the letter G in there. Okay? Don't put 19.6 here. Okay? They want 2G. Okay? Because we have to spend a ton of time going over tests, unfortunately, I haven't said that. All right, part B wants to know the net force in the, I guess what we call the Z direction, right? The direction out of the table. So that was 0, right? Once it's on the table. Part C, you had to come up with an expression for the normal force. Does anybody need me to run through this? That it's mv squared over capital R? Okay, cool. All right, so question D. Derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained a speed of v. So our drawing looks like this. You've got this, it's come down this ramp and then it's going around a thing, right? So the block is right here, and so at that instant, your overall force is this way. I'm going to do what I just told you not to do. There's a normal force pointing this way, providing a centripetal force, and there's a frictional force pushing backwards, opposing the velocity, right? what do we mean by tangential acceleration? You guys understand that? Because there's two types of acceleration here, right? Centripetal or radial, because they're equivalent, right? They mean the same thing. And tangential. So which one are we worried about? We're worried about tangential, but what does it mean?
It's the acceleration of force of friction.
Yeah, it's the acceleration, the instantaneous acceleration in the direction it's moving in. Okay? For us, it's going to translate to how quickly it's slowing down, right? We're worried about the change in speed, not the change in direction. The radial acceleration is a measure of how quickly it's changing direction. Follow? Okay? So, my acceleration tangential, what name for me the force that's producing the tangential acceleration? Friction. Does that make sense? Okay? So, let's see. Well, friction is, oh, well, that's coefficient of friction times normal force. So coefficient of friction times normal force over m. Be careful that your mu's and your m's are distinguishable. And then just substitute in, right? So you get mu over m times mv squared over r. The m's cancel, and you get mu v squared over r. There's our tangential acceleration. Cool? And I think, if I remember right, without looking at the answer key, I think that it was 3 points. A point for recognizing that the tangential acceleration was produced by the force of friction. A point for recognizing that the force of friction is coefficient times normal force. And then a point for substituting in your normal force and simplifying. Is that right? All right, so questions with that? All right, part D. This is something that, if you've seen this before, you've seen it in math class, but I don't think we've seen it in here. All right, so this is tricky. All right, so let me read it. Question E says, derive an expression v of t, derive an expression for v of t, the speed of the block as a function of time after passing point P on the track. So, over here at some point, come up with an expression for the velocity at time t. Okay? So I could solve this expression for v, but time doesn't show up in here anywhere, does it? So I need to find a way, doing part, what are we on, E?
Yeah.
I need to find a way to, I need to find a way to take this expression, which deals with the velocity at a given time and the acceleration at that time, and somehow inject t into there. So what's the connection? What does time have to do with all of this? Velocity is, I agree, change in position over time, but that's actually average velocity. And position's sort of not already in there, so that would just be introducing a new variable and would be getting rid of velocity, which is the variable we're interested in. What do you got?
Integrated in terms of t.
Okay, yeah. I guess that amounts to the same thing. Yeah, integrating in terms of t. What's the integral of acceleration with respect to time? Velocity, right? Okay, so I think that works. But then you would have to integrate this side with respect to time also, and that's going to get ugly because this is v of t squared. So you're totally in the neighborhood. We need to think in terms of integration, okay? But here's the trick. Before we get to integrating, we got to find a way to put t in here. Follow? So
I was just thinking, you just said a instead of a, you just put in dv dt.
there you go. Exactly. That's exactly right. Yeah, we need to find a way to put t in there. And acceleration is dv dt. Okay? So let's rewrite this expression. This becomes dv dt equals mu times v squared over r, right? So now I need to separate my variables. I need to get all of my v's on one side and all of my t's on the other side. Okay, I believe that process is called separation of variables.
Yep.
I'm bad. I know how to do math. I often don't know the terms for it. All right, so I'm going to multiply by dt and divide by v squared to get this expression. dv over v squared equals mu over r dt. Follow? Okay, so I need to integrate this mess. What are we trying to do? We're trying to find the velocity at a given time t.
Integrate the left side of progressive velocity, the right side.
Yeah, exactly. So we're going to integrate. So the bounds on the integration are the tricky part. All right. So watch this, you guys. So this side, everything is with respect to velocity. This side, everything is with respect to time, right? So I'm going to integrate both sides, but I need to make sure that I appropriately choose my bounds of integration. Okay? So let's do this side first. I want to know that if I start at time 0, once my time gets to t, what the velocity is, right? All right? Well, at time 0, what was my velocity? v0. And at the end of time t, my velocity is going to be, v of t. That's what I'm trying to find. Let me pause there for a minute. There's a lot going on there. That's some calculus. So do you guys understand that process? Have you guys seen that enough in your AP Calc classes that you know what's going on there? Okay, cool. So now we just got to integrate this mess. So this is v to the negative 2, right? So I believe that integral is going to be what? Negative v to the negative 1, right? Evaluated between v naught and v of t equals over here, but not really, right? None of this depends on t, so the integral is just mu rt. Or sorry, mu t over r, right? Evaluated between 0 and t, so you're just going to get u over r times t, right? Make sense? All right, and over here I've got, let's see, negative 1 over v of t minus negative 1 over v naught, right? Cool? And then algebra and solve for v of t. Do I need to go through the algebra, or is that good up to there? So to me, this, oops. Oh my gosh, this smartboard is going to be my death. That's the tricky part. Replacing the acceleration with dv dt so that you get the variable that you're looking for, in this case t. Cool? All right, now, take a look at the way these points are assigned, you guys. This part E was 3 points. If you look at the point distribution, that's the problems, not the answers. How do I lose papers so fast? Yeah.
So for D, when I solve for A, I actually just set my force of friction to be just in the negative direction, just because.
Sure.
Is it okay if my math ended up being different just because there were some negatives in there?
You know what? Yours is better. I should have made it negative.
Okay.
I totally should have made it negative. Yeah, because the way I've got it set up, my velocity is going to increase. I forgot that negative sign. I should not have abandoned my notes. Yeah, no, that's huge. You're correct. I'm wrong. Yeah, we need that negative sign in there. Right? Because your velocity is decreasing, right? Which up to here isn't that big of a deal, but the idea is we want our final velocity to be less than v naught. The way that I did it, it would end up being bigger than v naught. So I'm super glad you said that. I should have been more diligent in looking at my notes. So here, let me do this. I'll full screen it so that you can see the whole thing. The entire page. Is that too small? Negative, negative. So the blues are the add-ins. Thank you. Really glad you said that. Yeah, I have it here in my work, but I didn't put it on the board. So thank you. All right, now points. So the points for this, you guys, here we go. So 1 point was given for just substituting dv dt in for the acceleration. Okay. The next point was for including the negative sign. Okay. And then the third point is for doing the integration. So if you're freaked out by the integration, at least set it up, and worst case scenario, you lose a point. You know what I mean? Cool? All right. Cool. Cool. Any questions with this? All right. Finally, any other problems on number 2? I think we hit all the main points, yeah? All right, so finally, number 3. I know Kurt asked about the last one, 3D, I think it is. Does anybody need me to do A, B, or C? Didn't get C right either? Okay.
I got VO over 20B.
Okay. Instead of 30. Okay. Anybody need A or B?
You should probably do B, because I think the 30 came from B.
Yep. Why don't we just do the whole thing? It looks like, well, A is just a kinematics thing, right? Does anybody need me to do A? Going once? Twice? Okay, so we got to start at 3. This time I'll keep my notes handy so I don't make another mistake like that. Okay, so. All right, so 3B. So this is the one, we've got this disc sitting on friction. Is it frictionless ice? No, it can't be frictionless ice, because otherwise the stone wouldn't stop, right? So assuming the disc is free to slide on the ice, derive an expression for the speed of the disc and the person immediately after the stone is thrown, and then derive an expression for the time it will take for the disc to stop sliding. Okay, so here's our drawing. So we've got this big disc with a dude on it and a stone, right? Okay, so disc and dude, stone. All right. So what's the velocity of the disc and dude initially? 0. What's the velocity of the stone initially? 0. And therefore, my total momentum initially is nothing. Follow? So then the dude throws the stone. Action, reaction. He pushes stone forward, stone pushes him backwards, they're going to slide apart. What kind of problem is this? I've already given it away. Conservation of momentum, right? Okay? So I should be thinking like this. I should be thinking that my total momentum before the dude throws the stone has got to equal to the total momentum after the dude throws the stone. So 0 has got to equal mass of the dude and the disc times the velocity of the dude and the disc plus the mass of the stone times the velocity of the stone, right? And something here needs to be negative. So I'm going to assume positive, negative. Cool? So let's see. What do we know? So the mass of the disc and the dude. Well, let's see. The mass of the disc is m. And the mass of the dude is m over 2. And we're trying to find their velocity. Right? And then the mass of the stone is m over 20. And the stone is thrown with a velocity of v0. Cool? So I'm wondering, Alex, if maybe you counted just the disc and the stone and forgot the person?
I got B right.
Oh, did you?
Yeah.
Oh,
I did this.
okay. All right, so this is 3/2 m times v of d and d plus m over 20 times v0 equals 0. Algebraify, your m's cancel, solve it, and you get that the velocity of the dude and the disc is, what did we decide? Negative v0 over 30?
Yep.
Is that right? I left my science now since I botched that before. Okay. How's the question worded?
You don't need it because it has to speed.
Right, okay, yeah, so you don't need the negative because it says speed, right? Okay, so everybody good up to there? All right, part C, derive an expression for the time it will take the disk to stop sliding. So the idea is, technically speaking, the disk is going to fall, so it's going to gain vertical velocity, right? But when it hits the ground, the ice is going to take away that vertical velocity, but it'll still maintain that horizontal velocity, right? Stone. The stone is the thing through, standing on the disk. I may have did I misspeak?
No. For a second, I thought it was just held out.
Gotcha. What's up?
So then why is the disc falling?
I think I misspoke. I think I said disk when I meant stone.
Oh, okay. Yeah.
Sorry. Oh, right. That's okay. So I'm sorry. I got myself confused. I was thinking we were trying to find the time for the stone to stop. We're not. We're trying to find the time for the disk to stop. So I was speaking nonsense. All right. So we need to find the time that it takes for the disk to stop. Describe for me the force that's going to stop the disk from sliding, you guys. Friction, right? So here's what we know. We know that our initial velocity is negative v naught over 30. We know our final velocity is 0. Let's see, what else does it tell us? It tells us that our coefficient of friction is mu. So that means that our force of friction has got to be mu times our normal force, right? Well, our normal force is just the mass, which is 3/2 m. Why 3/2 m? Because the guy's still standing on it, right? Times g, right? Good? So that means that the acceleration produced by the friction is going to be the force of friction over the mass, right? So basically your mass cancels out. So you get 3/2 mu g. And now I am worried that we're going to not get 30.
That's what I did.
I just got A equals mu g. I have force of friction equals ma, and then
Did you include the
That's
gas?
right.
You know,
it's been umg equals ma.
how did you get rid of the guy's mass?
Oh wait.
Yeah.
You should include the guy.
Yeah, you can.
Answer key doesn't.
Oh,
No, wait.
I'm dumb. What did I do wrong? Did anybody see it? What's accelerating?
Block is decelerating.
The
Or not block, yeah. This.
the disk and the dude, right? So the 3/2 cancels also. Cool. Does that make sense, you guys?
Oh yeah, I see how I just set force of friction equals ma, and then solve.
Yeah, the mass is canceled regardless. You've got the same mass for your normal force as you do for the friction, so everything cancels.
Yeah.
Yeah. Okay. Are everybody good with what happened there? I apologize. And I just went through this fifth hour. I don't know why I keep making these little mistakes. I'm sorry. All right. So is everybody good up to there? All right. So now, what are we trying to find? We're trying to find the time, right? So then time is Vf minus Vi over A, right? Right? So Vf minus Vi is going to be V naught over 30 over mu G, so mu G, right? Is that right?
Yep.
Cool, you guys? All right, so should we jump ahead to D? All right, so D is kind of the same thing, to be honest, you guys. It's the only difference is now, instead of talking about sort of translational or linear momentum, now we're talking about angular momentum, right? Because you've got this disk, he's standing on the edge of it, so when he pushes the stone is going to push him, it provides a torque and makes the disk spin, right? Okay? So, to do part D, so if you guys understand the drawings like this, here's the disk, here's the dude, he's going to throw the stone that way, right? So before he throws it, what's our total angular momentum? 0, right? Does that make sense? Okay? So I need to ensure that after he throws it, the angular momentum of the disk plus the angular momentum of the dude plus the angular momentum of the stone, that's going to all add up to 0. Make sense or no? All right, so L for the disk. Well, it's a disk, right? So I for the disk is mr squared over 2. I guess I should write 1/2 mr squared. So that's the way we usually write it. Does that make sense? All right, now, angular momentum of the dude. Well, basically, the dude can be treated as a point particle traveling in a circle, right? So that's either mrv, or, remember, the angular momentum of a particle is mr squared, right? But what's his mass? Right? So you've got, oh shoot, sorry. I forgot my omega here, didn't I? Sorry. Does that make sense? Okay. Plus, his mass was m over 2 r squared times omega, right? Good? Yeah?
Why does it want half mr squared?
It's the equation for the rotational inertia of a solid disk.
In the question it gives you the rotational inertia of mr squared. Oh wait,
Over 2.
Gotcha. Sorry.
that's okay. That's not bad.
That's funny because I wrote it on in my notes as mr squared over 2. I was like, why did I write it that way? We always do 1/2 mr squared. So I'm sorry. All right, so is everybody good up to there? All right, now, plus the angular momentum of the stone. We can do mr cross v, can't we? But notice, what's true about my r and my v? They're perpendicular. So this just becomes the mass of the stone, which is m over 20, times r times v naught. Make sense, you guys, or no? All right, and I think that's it. I think you just solved that, right? And then you got to solve for omega. So let's see. You can divide through by m, and the m's go away. Kabam, kabam, kabam. So now I've got 1/2 r omega squared plus 1/2 r omega squared. I'm saying the squared in the wrong spot, but you know what I mean. What's up? Oh, you can cancel an r, yeah. So r, and r. Put x's through those things. Cool. So 1/2 of r omega plus 1/2 of r omega is just r omega equals v naught over 20. Is that right? Oh, negative v naught over 20.
Why would you want to?
You would have to have some information about the amount of time it took him to accelerate the stone from rest up to v naught.
He said it was, the problem said it was like negligible. The time it takes to put a one negligible.
So anyway, so solve this, and your omega ends up being negative v naught over, what, 20r? And the negative is just indicating direction. How is the problem worded? Derive an expression for the angular speed. So you just don't worry about the negative. Right? Because that's arbitrary anyway, right? Good? Problems with it? Okay. Let's see. So E says the person now stands on the disk at rest r/2 from the center of the disk. So in other words, instead of him standing at the very edge of the disk, he's going to stand halfway between the center and the edge. What's that going to do to his? Is this a question or an answer?
Yeah, it's a question. How come the stone is angular momentum? Can you, like, is the value of electric momentum and angular momentum interchangeable?
Say that one more time. Say the last part. Is the value of
Yeah, so
angular and linear interchangeable?
divided n times v of the stone.
Yeah, it's not the same thing. Yeah, it's not the same thing.
But the stone isn't moving in a circle, so how would I?
Yeah, it doesn't matter. So we.
At the beginning of the unit where you have like the jumper equations.
Yeah, so we talked about this. I don't know if you guys remember. There was a problem that we did where.
Wait, is L equal to R cross P?
Say that again.
What's equal to R cross P or something like that?
R cross
Or maybe it's
V
mass times R
is
cross
a jumper. No, V is R cross omega. Why am I R cross V?
R cross V times M is that L?
Yes.
So I just did take in, because I got the same answer, but R squared in the bottom.
Gotcha. Yeah. Okay, so to answer your question, the thing doesn't have to be moving in a circle to consider angular momentum. All right? To have angular momentum, here's what you have to have. You have to have a point about which you're trying to find your angular momentum. You have to have an object at some location with a velocity. So maybe my velocity is, I don't know, this way. Okay, so there's my velocity. So this object has some mass. It can be measured to be some radial distance away from it. And so even though it's moving in a straight line, at that instant, we can consider it as having angular momentum about this point.
It's like rotating on like actual axis. It has to be like changing an angle like, regardless.
Right. And the example that I gave you guys that I think helped was the thing where, where's the meter stick? Where we talked about, all right, here's my pivot point, here's my thing moving. Right? So the angular momentum of this gets converted to the angular momentum of the meter stick.
That makes sense.
Cool? All right. Question E. So what's going to happen if the dude stands closer to the center? He's going to have less rotational inertia, which means the disk should spin faster. It's the figure skater pulling your arms in. That's exactly right. Good? All right. So, your task over the weekend is to see if you can start tackling some of the chapter 15 stuff, all right? We'll finish up notes next week. I haven't graded them yet. Because so many people are out because of, almost everybody's taking it now, so I'm going to probably grade them. Sorry. It seemed like, what did you think about it?
I thought it was good, except for some of the equations. I've done the homework like closer to school, so it's been a long time, and then I realized I forgot to learn the equations.
I got it.
But besides that, I think.
Okay, did she need it over the weekend?
No, I don't think so.
Okay. All right, cool. Thanks.
Yes.